The electromagnetic spectrum is a chaotic mess of overlapping signals. To do anything useful with an electronic device, like pulling deep bass from a music track or isolating a single radio station, we have to filter out the noise by resolving it into a single clean line at a precise frequency. In this video, we are going to build 3 essential circuits on a breadboard: the low-pass, high-pass, and band-pass filters, and we will calculate the exact math needed to target your specific frequency. We are focusing strictly on passive filters today. That means we won't be using operational amplifiers to provide external power or voltage gain. We are relying entirely on the physical properties of resistors and capacitors. Mastering these 2 passive components is the first required step for hardware design. They form the physical foundation for audio engineering and modern signal processing. This is the low-pass filter. Place a resistor in series with the input and a capacitor shunted to ground. Cutoff frequency, where power halves, equals 1 divided by 2 pi RC. A 10 kiloohm resistor and 0.1 microfarad capacitor drops the curve steeply at 159 Hz, rejecting higher frequencies. Audio engineers use this exact schematic in speaker crossovers to strip out high-frequency vocals and route only the low-end spectrum directly into subwoofers. The resistor and capacitor work together as an electrical dam. They permit slow oscillations to pass to the output, while aggressively bleeding high-frequency interference to ground. This schematic shows the high-pass filter, and creating it requires a single physical inversion. You swap the component positions on your breadboard. Your capacitor moves in series with the input, and your resistor is moved to ground. This orientation is a common failure point for beginners. If you accidentally build the low-pass layout when your math intended a high-pass, you will completely block the exact signals you are trying to isolate. Built correctly, the high-pass circuit blocks steady DC voltage offsets from mixed signals, or to protect delicate speakers by cutting out subaudible microphone rumble. Look at this inverted frequency response profile. By simply swapping 2 physical components on the board, you use the exact same mathematical formula to produce the opposite physical outcome. This diagram shows a band-pass filter. We construct a cascaded layout by feeding the output of a high-pass stage directly into a low-pass stage. This requires a strict condition. The cutoff frequency of the high-pass first stage must be lower than the second low-pass section. This creates a targeted frequency window that is highly useful in medical equipment. An EEG machine uses band-pass networks to isolate specific physiological spectrums, like alpha or beta brainwave rhythms, ignoring the surrounding electrical noise in the room. By cascading these stages, your circuit stops acting like a simple wall and becomes a precision tool designed to extract specific data from a wider, noisy spectrum. This graph shows the band-pass profile. To tune it, we calculate the center frequency, or F0, the exact geometric mean between our lower cutoff limit, FC1, and our upper cutoff limit, FC2. The mathematical distance from the lower to upper limit is your bandwidth. To measure bandwidth sharpness, engineers use the quality factor equation, Q equals center frequency divided by total bandwidth. In this spectral profile, we visualize that selectivity. A higher Q factor indicates the resulting passband curve is narrower and sharper relative to its center. If your specific system requires extreme signal clarity, manipulating this exact quality factor ensures your components hit those tight tolerances. This table summarizes the 3 frequency selective networks we've constructed. The physical rules are strict. Place a resistor in series with a shunted capacitor to isolate low frequencies. Swap them, capacitor in series, resistor shunted, to eliminate low-end rumble, and cascade them to isolate targets. You now have the component layouts and the formulas. Your next step is to calculate the specific resistor and capacitor values needed to design a custom band-pass crossover for your own audio setup. When you apply the right math to a handful of inexpensive components, you gain direct control over the signals passing through your hardware.